Hi, Science 30s. This is the first lesson from the energy unit. So that is Unit D. We're definitely not going to get to Unit C just due to external circumstances. It's actually a really awesome unit. You can have a read through your textbook. There's some really cool stuff, especially in Chapter 2 with EMR and space and life cycles of stars and all of those things. They're quite interesting to learn about. But we're going to just finish off Chapter 1 of Unit D. You've already looked through Chapter 2 and did the sustainability of technologies, so looking at different sources of energy and how sustainable they are, how environmentally friendly they are, how economically beneficial they are, and those sorts of things. So if I haven't got your Chapter 2 stuff, there was a booklet of questions and then the sustainability analysis. Make sure I do get those kind of before the week of June 8th. I think I've got most of them already though. So Unit D, again, energy in the environment. So Chapter 1, let's see what I can figure out here. I did press record, yes. Okay. So hopefully you've printed off those notes that I sent already, or if you want to just follow along, whatever works best for you. But I know sometimes writing is helpful, especially when we get to some of the practice questions. There is some math in this unit, so when we're looking at some of the calculations, so you'll need to either have some scrap paper or have a printed copy of the notes as we go through. So the first topic, and again, this is supported by the stuff in the textbook. So have a read through the stuff in the textbook if you want a little bit more information to see some different visuals and so on. So the first topic that they kind of talk about is global energy demand. And so there's some graphs on the side of your notes. I don't know, did I put them lower in this? Nope. They are just gone. So there's some graphs down the side of this front page. So it's looking at three different things. So world population, and it's looking how the population has grown from 1850 to 2000. And we know that the trend continues. We're now up, I think about 7.7 billion, if I'm not mistaken. World energy use in exajoules. So again, joule is a unit of energy. Exajoule, 1 exajoule is 1 times 10 to the power of 18. So that's 18 digits after the one there. Big number. Again, that's world energy use from 1850 to 2000. And per capita energy use. So how much energy each person, or an exajoule per 1 billion people, is how that graph is measured. Again, 1850 to 2000. And we know that the trends continue, probably even get a little bit steeper from 2000 to 2020. Sorry, I've got the tickle in my throat. So the the world population is growing at what's called an exponential rate. So what that looks like in terms of a graph is if we have time here and number of people. Sorry, I'm writing on this tablet and it's sometimes a little bit of a pain. So number of people in time, what it actually kind of looks like is the start of kind of a, it doesn't loop back, but we call this a J-shaped curve. So an exponential curve where it's increasing more per unit time as we move along that x-axis. We know that as the population of the world grows, the demand for energy grows with it. So as there are more people, there is a higher demand for energy. And with that, if we need more energy, if we need more energy, we need to have more efficient energy use. So we need to be getting basically more bang for our buck, more energy at a lower cost, again, since the demand is going up. So right now, most energy that we use comes from non-renewable resources. So coal, other petroleum products, natural gas, oil, etc. Those are non-renewable resources. as demand exceeds the supply, so once we're asking for more than we actually have, these resources will run out. So if you're using it at a greater rate than can be maintained, eventually the resources are going to run out. We also know that our dependence on machines is increasing. Sorry, let's see disappear. So instead of farmers kind of pulling their crops by hand or using a horse with something on the back of it, now they have big tractors that are doing that type of work. And so again, that requires some of those non-renewable resources. And you can think about anything with machines. So we're not using just the regular old physical feed me food and I'll do work, but using machines which require electricity or other sources to supply them. So we know that the rate of energy consumption is increasing, especially in developing nations. So as nations are developing industry and becoming more and more reliant on machines and stuff, they actually are really increasing their rate of consumption. Our rate of consumption is relatively stable, 10 years to the next, but if you look at nations that are developing, it's actually increasing significantly. Sorry, I need to cough. So burning fossil fuels for energy is an environmental concern. So this is what we would have seen in that chemistry unit, right? So burning fossil fuels for energy is going to release a lot of greenhouse gases, resulting in global warming or global climate change. We know that a lot of factories can be releasing sulfur oxides and nitrous oxides or nitrogen oxides that can contribute to acid rain or other environmental impacts. So it would be good if we weren't so reliant on fossil fuels, but right now it's definitely the majority of what is being consumed for energy. And so you can look at those graphs and see that that's kind of reflecting those first couple of sentences. The population is increasing, global energy use is increasing, and again, per capita energy use has been increasing. If you look in the last, so 1980 to 2000, it was kind of declining or relatively stable, and we'd see that trend kind of continuing. Actually, we'll explain that in a couple of points. So the next one is, where's my cursor? There we go. Sustainable development is the management of natural resources that we can meet the needs of the present generation without compromising the ability of future generations to meet their own needs. So this is saying we're doing what we need to meet our needs, but we're not impacting future generations. We're not using up everything and saying, you guys better figure this out. So that what we need is sustainable development, something that can go on for an extended period of time. So overall, global energy consumption is not equal. So if we look from country to country, if we look across continents, across the oceans, there's lots of differences. Sorry if that was so loud. So developing countries have about 75% of the world's population, but actually only use about 30% of the world's energy. And so industrialized countries like us, about 25% of the world population, that should add up to 100, and use about 70% of the world's energy. So industrialized countries use a lot more energy, and like I was saying up above, developing countries are moving towards this kind of full industrialization. So if you think about it, that means that that energy demand is going to increase further. So per capita, this is kind of social studying a little bit. We're going to talk about GDP a little bit, and per capita, you would have learned about in Social 30. So per capita means per person energy has leveled off since the 1980s, but that's kind of misleading. So that's saying per person, we're using about the same amount of energy, but that's kind of misleading because the world's population has grown drastically still since the 80s. So it's not saying our energy use, it's saying our per person energy use. But if we're adding more people, that's a significant amount of energy. That's basically a big demand on everything. So GDP you've seen before, that's gross domestic product. It is an indicator of a country's economic activity. It's measured in billions or trillions of US dollars so that comparisons can be made across countries. So it's not just measured in the local currency. They use kind of a overall currency that they need to convert to and look at what's happening within a country in order to figure out what their economic activity is like, or what are they moving in, what are they producing, and so on. A measure of a country's GDP relative to its energy use is called energy intensity. It's calculated by dividing the energy used by a country in 1 year by the GDP. Countries with a higher proportion of high-tech or service industry tend to have low energy intensities, whereas countries involved with basically natural resource stuff, so extraction, refining, or just the development of natural resources, are highly energy intensive, so require a lot of energy. And yes, you're producing energy products out of that, but usually it requires a lot for that as well. So you can peek in your textbook on these pages and identify 4 factors that affect energy use. Just write a short little thing or write the words there. Energy efficiency. So this is something that you would have seen in Science 10 when you were looking at kinetic versus potential energy. We got our efficiency formula, and that's actually in your data book. It's on the first page that actually has information. So percent efficiency, it's in the data booklet like this. We'll talk about what it means in just a second. So from the law of conservation of energy, again in Science 10, we learned that energy is neither created or destroyed, only changed or converted in form. And so most energy transformations actually involve a loss of energy as heat. So it's not that the energy is disappearing or being destroyed, it's being lost as heat. It's not a useful output. So the example that I talk about a lot is incandescent bulbs, so kind of the more old school light bulbs. I still have lots of them kicking around in my house as we replaced the more efficient ones. So an incandescent bulb is about 5% efficient. So that means for every 100 joules of energy that go into it, only 5 joules actually go towards lighting the light bulb. That's 5%. The other 95 joules are lost as heat typically. You've all probably touched a light bulb at some point that was recently on for an extended period of time is hot. You all maybe have also heard, definitely in our classroom, and I even have a couple at home, lights that make like this weird buzzing sound or screeching sound. That's waste energy. Your light doesn't need to make sound. All that it needs to do is light up a room. But it's not very efficient at that. I think the LED light bulbs that are being used now are something like 40% efficient. I'll look that up in a bit. Um, Still not, nothing's going to be 100% efficient. There is always going to be loss of energy as heat or light. So what we can do is calculate the efficiency of things. So useful output energy is the proportion of energy transformed into a desirable form. So for those incandescent bulbs, this is our useful output. Unless you're intending for your light bulb to heat up your bedroom, you don't actually need heat. So this is our useful output. The input is the input is the energy required to operate the device. So what you're putting into the device, the machine, whatever's plugged in, whatever it is. So energy efficiency is the proportion of input energy that is converted into useful energy. So that's your output. And it's expressed as a percent. So this is our formula for this one. So percent efficiency is equal to useful output energy divided by input energy multiplied by 100 to get it as a percentage. So the two questions below this chart are efficiency calculations. So maybe just pause the video and try filling out this table. So what energy are we putting into these devices? What do we want coming out? And what's the typical waste energy in this case? And then try calculating these two. So pause the video. I'm going to go over it in a bit. So try pausing the video and give it a try, and then I'll go over it. And I'll drink coffee, even though I'm just expecting you to pause it. Okay, so a light bulb. The input energy of a light bulb is electrical. So that is a form of kinetic energy as electrons are flowing through the circuit. Your useful output energy is light. And waste energy is thermal or heat. A car engine. So you're actually putting in chemical potential energy, so the energy that's stored within the bonds of your gasoline or whatever petroleum product it is. Your useful output energy. So what do you want your car engine to do? You want your car engine to move you. So you want it to turn into kinetic energy. And again, your car heats up, your engine makes sound. Oven. So it depends. We'll talk about or some people have gas ranges. Mine's electrical though. I love cooking on gas. My next house will have a gas range and oven, and yes. So electrical is the input energy, so it's plugged in, it's drawing electricity, and the useful output in this case is actually heat. You want your oven to heat up, you want to cook your food. The waste energy, this one's kind of hard to think about. If you look in your oven and you look at the bottom, there is a little bit of light produced, right? Those coils of your oven, those coils at the bottom, the element actually kind of turns red. It emits light. You can also say that the waste energy, some of the waste energy is thermal, because not all the heat that's produced within the oven actually goes to cooking your food. So there's some of it that's wasted. It's not 100% efficient at every joule of energy that goes in cooks your food. There's just heated air within it that's not actually cooking your food in the end. Television, again, electrical, it's plugged in, flow of electrons. Useful output is visible light, right? You want your TV to make sound too, but it does also heat up a little bit. You might have some other proposals of useful output or waste for some of those. They might be right. Some practice problems for calculating efficiency. So it says calculate the energy efficiency of a water heater that uses 200 joules of energy to increase the thermal energy of water 55 joules. So this is your hot water tank. So it requires energy, electrical energy. Actually, no, it would be working off chemical potential because natural gas would be heating it up probably. There are electric ones though too. So this is just an efficiency question from this equation up above though. So percent efficiency is equal to useful output. I don't know why this is being weird right now. Useful output divided by input energy multiplied by 100. So the useful output. So it's increasing the thermal energy of water 55 joules. So that's what we want. We want to increase the temperature of the water. It requires or it uses 200 joules. So that's your input energy. So your smaller number is always going to be on top, your bigger number is always on the bottom because you can't have the bigger number on top, right? You can't have more energy coming out than you put in that has energy being created. So that will always be the arrangement of that. So once you calculate it out, it's 27.5% efficient. So this next one, it says if an automobile is 20% efficient, calculate the useful output energy from 1 kilogram of gasoline containing 44.5 megajoules of chemical potential energy. So what we actually need to do is rearrange this formula. It's asking us for our useful output energy. So what it's, oh, I pressed something and now, come on. So it's asking us to rearrange our formula to solve for this. So in order to rearrange that formula to solve for that, we need to divide by 100, whoops, on both sides of the equation. What am I doing? I'm trying to write with my touch on my computer, and we need to multiply both sides by input energy. What you do to one side of the equation, you have to do to the other. So now we have input energy multiplied by percent efficiency divided by 100 is equal to our useful output energy. Oh no, I left it as yellow. Please no yellow. Okay, so again, percent efficiency. I don't know why my smart file is being so slow. Percent efficiency multiplied by input energy divided by 100. So percent efficiency is 20%, input energy 44.5 megajoules. You don't need to convert that. Your answer is just going to be in megajoules from there. Divide by 100. So that gets us 8.9 megajoules of energy. I'll write that quick once my screen decides to start being a friend. So our rearranged formula is percent efficiency multiplied by our input energy divided by 100. And so when you would substitute that all in, you get 8.9 megajoules of energy of output, of useful output. So that's how you calculate efficiency. We're going to do just part of the next page with this lesson, and then the next lesson will be your harvesting chemical energy. So this one's called solar fuel from the past. So we know that the source of all energy, the original source of energy on Earth is the sun. So it provided light to those small photosynthetic organisms that died and got buried and compacted under layers of rock and created these fossil fuels and petroleum products. So the original sun was the source. Well, I've filled in most of this. So the original source of almost all energy, including energy stored in plant material, is the sun. And again, photosynthesis was forming that chemical potential energy. So the first widely used form of chemical potential energy was actually wood used for cooking and warmth. So burning a pile of logs, you could cook food over it, make it not kill you, and you could warm up. So as populations grow and industrialize, new fossil fuels have been found to meet energy demands. And so the big one is coal. So coal is a carbon-rich mineral found in Earth's crust. It was really big in steam engine times. And right now, coal actually generates 70% of Alberta's electricity. I think that's actually decreased a little bit in more recent years, but it would still be way, way up there. So again, peek at these two sections in the textbook and just answer those questions. The next one, another fossil fuel or fossil product, is petroleum. And that became the world's primary fuel in the 1950s, mostly due to the impact of the automobile on society. So extraction and refining of petroleum products to produce gasoline, but also to produce jet fuel and asphalt and all those different things that can come out of the fractions of petroleum products. So think about how petroleum is made and extraction. Why is it so expensive? That one's a big question. Another fuel is natural gas. So what's used to heat your homes. So natural gas is a mixture of hydrocarbons primarily composed of methane. And so again, that's CH4. And it's the primary fuel for heating homes in Alberta. There's something called coal bed methane. So that's found trapped within layers of coal, and hydrate are new sources of hydrocarbon. So coal bed methane in Alberta, I think more so in Saskatchewan actually is coal bed methane, is a big thing that they're trying to extract safely. And something called hydrate are new sources of hydrocarbons. So as it says here, so during the process that makes coal bed methane is also produced. It also can be trapped between those layers of coal. And methane can also be found within ice as methane hydrate. And methane hydrate can actually also be found in the ocean. So not just like floating around in water, but when they're drilling in the ocean, so they're drilling down into rock, they find a lot of methane hydrate in there as well. So all of these products that we have up above are all fossil fuels. Oops. Which are considered to be non-renewable resources. In theory, they could be renewable if you have 250 to 400 million years to wait for the development. So overall, non-renewable. It's believed that well over half the world's petroleum supplies have already been used up. So that's, you know, since their development in the last within the last 100 years, we've already polished off half of it. And we know how the population has grown in the last 50 years even. Again, it's an exponential curve. So how fast are the remaining supplies of petroleum products going to disappear? Quite rapidly. So we know that we need to move towards different sources of energy. So sources that are renewable, sources that generate a significant amount of energy. And so again, in chapter 2, you would have seen the relative amounts of energy produced and the availability. Like in certain places, using solar panels is actually not going to be that useful, but maybe they have access to geothermal or tidal or different sources of energy. So that's going to be the end of this lesson. I will record the second lesson. There's not really any homework other than just reading the section and filling in those couple of questions. So we will see you or talk to you all later.